Hi, you're welcome to today's coding section for day 6. And today we'll be looking at how to apply explainability to our model. So let's dive in. So the first thing you need to do is to rename your script. So we have that as the 6, explainable, represented that as XAI, SHAP. So if you have followed us in our previous lecture, where I talked about why we need to apply SHAP, you understand that the application of SHAP is very important so that it can add more interpretation to the behavior of the model, or what contributing features led to the prediction outcome. Okay, so in every cell, the first cell, we have to import the necessary libraries. So here we are going to import SHAP. So just in case you did not do the installation of SHAP, all you need to do is to say pip install SHAP. However, if you have done that, just go ahead to start with import SHAP. The next we need to do is to import pandas, and we are representing that as PD. To import XGBoost as XGB. To import matplotlib.pyplot as PLT. So once we are done with the importation, the next thing we need to do is to load the data and train the model. So we have that as PD equals to, df, which is the variable, equals to PD, which is the pandas, to read the file, the CSV file. And the file we actually got the file after the feature engineering. So it's a process data already, which we did in our day 3. So you can make reference to the day 3 lecture and coding section. So once we're done with this, the next step is to indicate what is the X variable. So that means we are trying to remove the target variable and the timestamp from X. Okay, so for us to do that, it means we have to drop the features not important. So for the columns, the feature not important will be the global active power and the timestamp. Which is the date time. And here we have an unnamed column, so we are setting that 0. So let's close that. And remember to put the quotes. Now, we need to load the pre-trained XGBoost models, which is already saved in the JSON format. So if you recall, in our day 5, we actually saved our XGBoost model in a JSON format, which we'll be using here. So we have model XGBoost.booster, and then we are going to load the model. So the name of that JSON file is SGB underscore NHA underscore model.json. JSON file. Okay. So let's run each cell. You could do Shift Enter or just click here to run. So we have this error which says unnamed 0 not found. Okay, erase it and run again. So it's perfect now. Now, the next step we have here is to align X with what the model expects. So we have that as X logs and our square brackets taking all, and also we have X dot columns dot duplicated. So what this is going to do for us is to delete any duplicate column. And also to ensure that X in this is in the same order as the model feature names, we are going to write this line of code S columns that should be in square brackets. That's columns. And then we run that cell. So we want to save the original feature names during training. So if possible, so save if you're 100% sure X matches the training layout. So what code are we going to do? We are going to say model.features underscore names list S columns. And then in the next cell, just check what is in the X column. So let's run this. So we can see the S column. So I was trying to drop this, but an error popped out. So let's just proceed. Okay, so now let's apply the SHAP explainer and the value computation. So this variable explainer, we're going to use that. So the tree explainer, although we have two common types, the tree explainer and the kernel explainer. So we're using the tree explainer. So this will help us to create a tree explainer which is optimized for the tree-based models. For example, in this case, we're using XGBoost. Then our SHAP values variable has the explainer dot SHAP values X. Okay. So this is going to help compute the SHAP values for each feature in each row. So each value explains how much a feature contributed to a prediction relative to the mean. So let's run this, although this might take a long time. So while we are waiting, we could proceed to look at the plots. So we are going to, we've already imported matplotlib, so we should just proceed with creating the beeswarm plot. So we have sharp.pl plot.beeswarm, and then fix in the parameters. Here we are going to have the sharp explanation, where we have the values being the SHAP values, the data X being the big X, and then the feature names, which is the S columns. Now, for us to save the plot to a file, all we need to do is to say plt.save big. And then we name that as beeswarm for plots .png, which is the format we want, and bbbox, which is set as tight. Then the resolution, we are putting that as 300. So if you want it to be higher, the image resolution to be higher, you could use 600 for the DPI. Then if you are to show the plots, all you need to say is plt.show. If you don't want to show the plots, you just say plt.close. Okay. So let's fix in the other plots. So we are going to put in the bar plots, the dependency plots, the waterfall plots, and also the scatter plots. Okay, so let's proceed with the bar plot. So here we are going to have sharp.plots. Yeah, so let's see, we have an error here. So let me fix in this column. Let's see what the outcome will be. So you know, initially when I put the unnamed, it didn't work, but this time it's okay. So I'm running again. So please make sure you put back the unnamed, because we could see here that it has been modified. So it's considered that as the column I want to drop. So we can now see the importance columns we are using for X. Okay. So now we have let's proceed with other plots. So we have the plots.bar. Here we have the SHAP explainer values. SHAP, you can actually copy and paste from the previous beeswarm and just make some little modification. Here is supposed to be explanation, so take note of that. Just rerun it. Okay, so let's see. So also here for the bar is explanation. Sorry for the typos. And here we have data of big X, features, names, considering the X column. So having fulfilled this, we are going to run this cell also to prepare it for our bar plot. Okay, so let's move over to the waterfall plot. So for the waterfall plot, first, we are going to write this line of code where we have x.ilog and square 0. So this is going to keep the first row data frame. And our explanation variable will have the explainer for that sample. So SHAP explanation object with shape 1, n features. So we are going to use index 0 to extract the first and only explanation from the matrix by writing this code pl sharp.plot dot waterfall and then we have the explanation 0. So let's see what we have here. So there's an error here. So let's quickly fix that. So it says PLT, something is missing. So it's pointing towards here. Save. So let's see from here. That means we do not close this bracket. So let's run that again. And once we are done, we run back here, the next one, and then this one here. So take note, you're not supposed to run here. My fingers were too fast to click here. Just rerun here, here, here. And let's proceed. So while we are waiting for it, we'll just fix in other plots. So we have done for the waterfall. The next plot we need to consider is the scatter plot. Here, we are going to get the index of the feature. So we have feature name. We are considering the R cos, that's the cosine. And in this case, we need to look at the feature index variable, which has the s columns dot get underscore loc for the feature name. Now we need to build the full explanation object. Here we have the display sharp, which is the explanation. So let's see this. Something is missing again. The brackets. Okay. So let's see for the waterfall. Okay. And let's just continue with the scatter plot. Okay. So we have values, which is from the SHAP values. And we add more the data, which is the X values. We have the feature names, x.columns. Okay, and then we can go ahead to extract the explanation slides safely, so no series or in the array. So what do we do? So we have our sharp.plot, the scatter of our SPLY in square, considering all, with the feature index. So let me be sure that the brackets are complete this time to avoid typos. Okay, so let's see. I think something is modern here. Okay, so let's run this. Okay, so we've achieved the scatter plots for this. So if we were to get the dependency plots, it's a bit different from the scatter plot. So all we need to do is to call our sharp.dependence dependent plot, where we have this feature, our cosine, the sharp values, x, and the feature name of x columns. Then close the brackets. So let me take notes of this. This is supposed to be big X. Feature names, S column. So let's run. Dependence. That is supposed to be an underscore. Okay, so let's see how that's scaled through. So we're able to get this. Okay, so let me just give a quick explanation of this plots so that you can be able to understand what we have. So let's go through the first one, which is the beeswarm. So this plot shows the sharp values impact on model output for each feature across all samples in the dataset. So for the x-axis, the sharp value tells how much that feature pushes the model output higher or lower. So for the y-axis, features ordered by overall importance. So we can see two common colors here, which is blue and red. At this point, this is where blue and red mixed together to produce a purple color. So the blue tells the low feature value, whereas the red tells the high feature value. So what is the insight here? So apparent power and global intensity has the highest impact. So when apparent power is high, which is red, sharp values are positive, indicating higher model output. Features like R, plus, R, and submetering values are minimal, we can say. They are minimal contribution in comparison. So if we go to our next plot, which is the bar plot. So this plot ranks features by their average absolute sharp value, which is reflecting their global importance. So the apparent power is the most influential feature, where we have 0.63. Then the global intensity follows, but other features barely contribute to the model's output, as you can see. So you can see the apparent power 0.63, global intensity 0.19. So another one I want to talk about is the waterfall. So for the waterfall, we could also see the contributing factor, the value for the apparent power, and lesser for other features. And looking at the scatter plot, you can see that this considered only one feature, which is the R cosine. But in this place, it tells us the interaction features between the R cosine and the submetering 3. Okay, so is there anything more I would like to tell you here? So if we are looking at the dependency plots, this tells in color compared to the scatter plots. So the difference between scatter plots and dependence plots, like I said in the lecture, the scatter plot has to do with one feature, whereas the dependence plot has to do with two features. So in such a scenario, it tells us the relationship, the interaction effect between two features and how magnitude the impact of both of them are. So now, in summary, this SHAP visualization I've shown you with the code in this coding section. It tells more about visualization, which unlocks the black box in nature of machine learning models. So now you can be able to identify which features matter most globally, and you'll be able to understand how a single input affects a prediction. Now you're also able to explore time of day effect and feature interaction as seen here. And translating raw model results into explainable, trustworthy insights, which is an important skill you've grabbed today. So I'll be ending the lecture now. Thank you for watching, and I believe you've come to understand how we apply explainability using SHAP in our ML model in order to avert the issue of black box in nature. Thank you so much for watching. If you're just joining us for the first time, don't forget to like, subscribe, share with your loved ones, and hit the notification bell so you get notified on my new release. Have a nice time. I'll be signing off now. Bye.